Okay, thanks. Thanks for coming. And yes, so the title is From Möbius Inversion to Renormalisation. I think I will start quite slowly with Möbius inversion, and I think many of you already know all that. If it's too slow, you can look in a paper I have with the same title. So there's you can find a paper on the archive, for example, if you want to read ahead while I do the slow parts, which is about Möbius inversion. So let's start with the very classical Möbius function in number theory. So an arithmetic function is just any function from the set of strictly positive natural numbers to, well, let's say the complex numbers. So of course, when you call it an arithmetic function, the idea is that it should encode some number theoretical information, but really any function will do. So one of them is the zeta function, which has a very easy definition. It sends every number to 1. So why is that interesting? So whenever you have an arithmetic function, you can assign to it its Dirichlet series. So Dirichlet series, and I call this one f. I call it f tilde. So it's supposed to be a function on an open domain in the complex plane, and you sum over the strictly positive numbers. Then you put the coefficient here, and then you have this thing here. So that's the Dirichlet series, and you can see that if you take the zeta function, you get Riemann's zeta function. It's just 1, like this. Okay, so there's a whole. Is it too high now?
No, it's still visible.
Okay, good.
The right one is 20 centimeters, or maybe not visible.
Like this?
Yeah.
Okay. So the Möbius inversion principle says, this is Möbius 32. It says that if you have two arithmetic functions such that f is obtained from G by summing over all the divisors, then you can also write G in terms of f, like this. But here comes the Möbius function, where the Möbius function is 0 if n has a square, so a prime factor occurring more than once, or otherwise it's -1 to the r if n is equal to a product of r distinct primes. No repetition, because then we would be in this case. So that's Möbius inversion for arithmetic functions. Now, what is going on here? It becomes clearer if we introduce the Dirichlet convolution product. So let me keep this for a moment. So the convolution of two arithmetic functions, I need to say what it does to a positive natural numbers, and it is given by summing over all the products giving n, and then you evaluate f on the first and g on the second. So this is Dirichlet convolution. It corresponds to pointwise product of the Dirichlet series. So
for any f and 2,
if we have this relationship, then this. So now we can see that what actually is taking place here is that there's an invisible zeta function here. So what it really says is that if f is equal to g convolved with zeta, then g is equal to f convolved with the Möbius function. So this makes it much more clear what is the kind of structure involved here. So actually, the whole thing can be set by as follows, that this one is convolution invertible with inverse mu. So to make sense of this, I didn't tell you what's the neutral for convolution. The neutral is epsilon defined by 1 if n is equal to 1 and 0 otherwise. You easily check that this is neutral for convolution. So it makes sense to ask what is invertible. And what Möbius inversion says is that the zeta function is invertible and its inverse is the Möbius function. Okay, so that's all I wanted to say about the classical Möbius inversion.
Is that now the space of arithmetic functions with the algebra structure?
Once again?
What is the structure on the set of arithmetic functions?
It's an algebra for the just an algebra. But it's underlying this algebra is a coalgebra, and that's what we are going to see now that we come to Möbius inversion in combinatorics. So this is essentially Rota. There were some precursors in Weisner in the 30s and Hall also in the 30s, but Rota was the first to write it. So you start with a poset, and then you let C be the vector space spanned by the intervals. So an interval is the set of all elements in the posets between. And for this to work, we need all the intervals to be finite, and that's what's called a locally finite poset. So this is the vector space spanned by all the intervals. It becomes a coalgebra called the incidence coalgebra. So that means that it has a co-multiplication map. So it's the dual notion of algebra. So instead of having a map that multiplies two elements, it co-multiplies a single element and returns two of them. And since the tensor product of vector spaces is not just about pairs of elements, but sums of pairs, it's important that we work with vector spaces. So what does it do? It takes an interval and then it sums over all ways of splitting the interval. So you sum over all points in the interval, and then you take the first part up to the midpoint m, and on the right hand factor you put the other part of the interval. So that defines a co-multiplication on this vector space, making it into a coalgebra. There's also, so this is co-associative, which when you write it out is just the dual notion to being an associative algebra. It's also co-unital, and the co-unit is epsilon. So that's, well, here I take the ground field to be q, it doesn't really matter, but this is the function that sends an interval to 1 if it's a trivial interval and 0 else. So this is the incidence coalgebra of locally finite posets. Then you can look at the convolution algebra. So this is this vector space of all linear maps from C to the ground field, and it has a convolution product with neutral epsilon. So this is something you can do whenever you have a coalgebra. You can get an algebra structure on the dual by, well, the input is an interval, and the first thing you do is you use the co-multiplication to split it, and then you put f on one and g on the other, and then finally you multiply again. This is multiplication in the ground field here. So it just means that if f and g are functions, linear functions on the incidence coalgebra, then we can co-multiply them by evaluating on the interval by first splitting and then evaluating f on one and g on the other. So the formula is the sum over m, like here. You apply f on the first and g on the second part, and then you multiply in the ground field. So now we can state Rota's theorem. Well, first I should say, what is the zeta function? The zeta function just takes all intervals to 1. So Rota's theorem says that the zeta function is convolution invertible with inverse, and here comes the Möbius function. And the Möbius function can be described in different ways. This is the classical ways by Rota. It's 1 if it's the trivial interval, and if it's not the trivial intervals, then here comes a recursion. It says minus, and then we have to sum over all m in the interval, but we take exception from the last point, and then we take the Möbius function of x to m. So this is a recursive definition, that you define mu in terms of mu, but since we took exception from the case where m is equal to the last point, all these intervals are shorter than this one. And since we're talking about locally finite posets, when you do that, the number of elements times of the poset, you eventually arrive at the trivial case where the recursion starts. Okay, so this is Rota, but it's essentially the same formula that Weissner had found in a special case of, I think it was just for finite lattices or something. Another formula is the following. Is it too high now? A little bit?
A little bit, yes.
Okay.
Now it's good.
The other formula is the following. It says that you take, I write it first and then I explain it. Phi even minus phi odd. And what is phi even and phi odd? Maybe can you see if I write here? So phi even is the number of chains of even length from x to y. So even length. And then I leave it to you to figure out what phi odd is. So this second formula was first found by Hall in a special case, and it's also prominent in the work of Leroux. So there are these two main formulas for the Möbius function. So I will explain how to generalize these definitions to a place where you can cover renormalization. Maybe I wait a little bit with even and odd and just do a little bit of abstraction immediately. Namely, I would like to, I mean, this looks clearly like a convolution. So I would like to write this whole formula using only convolution. And then it becomes like this. Mu is equal to, and now I unpack. So there are two cases. If they're equal, then I put 1. That was the co-unit. I may have forgotten to write it or I erased it, but the co-unit is equal to 1 if they're equal and 0 otherwise. So that's the first case. And that does not give any contribution from the second case because it was equal to 0. On the other hand, in this case, where it's a non-trivial interval, then there's no contribution from the co-unit. So in this case, this is clearly a convolution. It's the convolution of mu with, and then here there's an invisible factor, that's the zeta function. But there was exception here. M is not allowed to be the last one. So that means that we are subtracting the case where m is equal to y. That's what this one does. Okay, so here is a very fancy way of writing the formula using convolution. And this is the one that I will continue with. Before we move on, I just want to give a few examples. Of Rota theory, which has really become a main tool in enumerative combinatorics. So let's just see some quick examples. So if you take this poset, all the natural numbers, then you can easily check that the Möbius function, well, I write it just like for 0, it's equal to 1 if n is equal to 0, minus 1 if n is equal to 1, and 0 otherwise. So how do you do that? Well, you just take this function and verify that it satisfies this recursion. So that's sort of a base example. The next example is the one we started with. You take the positive natural numbers, and then you take the divisibility relation. So that means that, for example, d divides n. So that's the one that gives the classical Möbius function. So how do we see that? We see that by observing that this poset is actually just an infinite product of these. So I write here an infinite product over all primes, and then I write this one. So the idea is that you take a natural number here and you write it as a prime factorization. And then the corresponding element in this product set is just the vector E2, E3, E5, and so on. So this should be a weak product, meaning that only finitely many factors are allowed to be non-zero. So you can write this poset as a weak product of these basic ones. And then you can, well, it takes a little bit of theory, but the classical Möbius function can now be written as an infinite convolution product of these. I erased it a long time ago, but the fact that square factors count as 0, that's just because as soon as you are beyond 2, you get 0. So if you just take the infinite product of all these, you get the classical Möbius function. The other very nice application that everybody knows is the inclusion-exclusion principle. And that you get if you take the power set of a fixed finite set X with inclusion of subsets. Then what you find is that the Möbius function of an interval from T to S, so there are subsets of this finite set X, is -1 to the number of elements here. So if you unpack that, that's precisely the usual inclusion-exclusion principle. And let me do a sub-example of this one, because just to see how you use it for counting purposes. So a derangement of a set, that's a permutation without fixed points. So how many derangements are there of a set with n elements? Well, you can sit down and fiddle with it, and it's not so easy as you might think if you just do it by hand and sit and fiddle. But it's very easy to solve with Möbius inversion. And I think that's a nice illustration of how it's used, because it's quite clear that the permutations of a set, well, that's a sum of all the derangements of subsets. Because for every permutation, you just say which elements are actually moved, and it must be some subset that is actually moved. So these cover all these.
Sure, you seem to have some lag right now on the recording. Thank you.
Okay, sorry about that. I should have plugged it in from the beginning. So clearly, any permutation has a certain set of points that are being moved. So all the permutations can be written as derangements like this. And now Möbius inversion immediately tells us the number of derangements, because that's here there was a zeta function invisible. Now I just have to write permutations of t, and then the Möbius function of s minus t. And the Möbius function we have here, and permutations are just a factorial, and you get a immediate formula for the derangements. Let me just look at the time. Okay, maybe I want to give one more example, just to point outside combinatorics a little bit. And that's an old application in probability theory. So let x be a random variable. Then you can define its moments. Just write like this. That's the expectation of the powers. They're the moments. And they do not always exist, but when they exist, they characterize the distribution completely. So if you know the moment, you know everything for calculation. Now, the Danish statistician Thiele introduced the cumulants. The cumulants, well, there are other quantities. They carry the same information, but they have the property that if you take a sum of independent variables, then you get the sum of the cumulants. So this is not true for the moments. So he introduced these, and they're characterized as follows. So the first cumulant is just the first moment. The second cumulant is the second moment minus the first moment squared. And the third one is phi 3 minus 3 like this plus 2 and so on. So Thiele gave formulas for calculating all this. And these this is the variance, as you recognize. This is some kind of skewness, and the next one is some kind of kurtosis, and they have some interpretation. Okay, so that's very nice. They determine the same information as the moments, but they are additive for x, y independent. So now that was a long time ago. So in the 60s, Schützenberger, Speed, and Rota, they observed that this is just Möbius inversion. And it's Möbius inversion in the partition posets. So how does it work? Well, you can write down what phi n is in terms of cumulants by summing over all partitions. And here when I write cumulant indexed by a partition, oops, that's just the product of all the cumulants of the blocks. So there's a zeta invisible here. So these formulas, they just come out by saying that the cumulants are the moments convolution, the Möbius function. And that's the Möbius function in this poset. And it has a nice formula. It's n minus 1 factorial minus 1 to the n minus 1. So if you plug this in, you will recover these things. So it's about counting partitions. So this is something important in probability theory, and it's just an example of Möbius inversion. Okay, now we should start abstract Möbius inversion. And also give some proofs. So you don't need posets to do all this. You can start with any filtered coalgebra. C. So it's a coalgebra first of all, and then it has a filtration, meaning a sequence of sub-coalgebras that exhausts the whole coalgebra. And then you demand that the zeroth filtration, so for this to be a filtration, that means that if you co-multiply something of filtration degree R, then you land inside the pieces like this. So the condition we need to impose is that the zeroth graded piece is spanned by group-like elements. And an element is group-like if it only has the diagonal term. Okay, in this situation, we can write down the Möbius inversion principle. So, as before, we have the convolution algebra. This one is equal to 1 if it's group-like, and 0 else. This is not completely precise, but it's good enough for now. So in Möbius inversion principle says that if you have a function such that all the group likes are sent to 1, then phi is convolution invertible with inverse, and I write it as psi, and now I will describe psi. So this is almost a proof by definition, that I just make a lot of definitions and that will be the proof. So I define psi 0 to be epsilon, the co-unit of the, and then I define the next one to be, I use this, minus epsilon. So now I have defined these for all n. Now I define the even to be the sum of all the even ones, and I define odd to be the sum of all the odd ones. Now here you may rightly worry if this is an infinite sum. It is an infinite sum of functions, but it has finite values for all x, because if you plug in here, for example, and see what does it do on x, and you assume that x is in filtration degree r, then this will be 0 if n is bigger than r. Because this convolution, what it does is first split out x into n factors. And since it has to go down in filtration degree, one of these n factors must be 0, of degree 0, if n is bigger than r. So if it's of degree 0, then it can be written as a linear combination of group-like elements. But on the group-like elements, these two agree, so that's the difference is 0. So even though this is an infinite sum of functions, it's still a valid function. On every input, it has a finite value. Okay, that was just maybe the only interesting remark. The rest is just definitions. So now it's clear that odd is the same as even convolution with this, because you just, if you have something even and you take one more factor, you get something odd. And also even is odd convolution this, except that we need to have 0 separately, because 0 is not plus 1 of an odd number, so we need to put this one here. Now we just take the difference between these two. So one more definition, and then I think we are done. So we just take the definition of these two. So that will give us an epsilon, and then it will give us odd minus even, but that's psi itself with a minus sign. So here I should put a minus sign and then psi, and then finally this factor here. So here we see at the same time the two formulas for Möbius inversion. Here I did not only invert the zeta function, I inverted anything with this property. The zeta function clearly has this property. So we see that the Möbius function, which would be the result, it gets the whole Leroux formula here, and it gets Rota-Weisner recursion here. So that's the abstract Möbius inversion principle. To see that it really inverts, you should of course take this and convolve it with phi to see that it works. But that follows immediately if you just move this minus sign to the other side and expand and simplify, you immediately get that it is actually an inverse. Okay, so this is the abstract Möbius inversion principle. Okay, now we are ready to go to quantum field theory. And I will see if I can keep this formula. So I don't know much about quantum field theory. So what I will tell you is really a cartoon of some of the algebraic structure. So in quantum field theory, you want to evaluate the scattering matrix. So that's, you imagine some particles coming in and some particles coming out, and you want to compute the amplitude of certain interactions taking place here. So this is called the scattering matrix. And perturbative quantum field theory make the following expansion. And that's the reason it becomes thoroughly combinatorial. Namely, you can expand this in a sum over all graphs. Then you have to put here the Feynman rules, and then you have to divide by the automorphisms of the graph. So gamma belongs to the set of all graphs. Here you write set. In a moment it will be a bialgebra, but and I would have to be a little bit more careful what I mean by all graphs, but it's a certain family of graphs, and oops, these are the Feynman rules, or Feynman amplitudes. So the idea is that the contributions of all these interactions become very small when the graph gets complicated, when it has many loops. So the idea is truncate at some loop number. So loop number, that's what physicists call the Betti number. So you truncate at 7 loops, and then you calculate all the Feynman amplitudes, and you sum it all up, and you get something that should be the total amplitude. Now the problem is that all these they are divergent integrals. For graphs with loops. So you get infinite quantities, and you cannot sum them. So renormalisation is the art of extracting a finite number from these infinite numbers. I think I will erase this. Please have it in your head. So renormalisation is to extract finite values for each graph. And this can be done in many ways. I will describe something called BPHZ renormalization, and it has the following steps. Step 1, you regularize. That's a standard trick, so you just change the definition of the Feynman rules so that they take values in Laurent series. So this is the physicist notation for allowing only finite negative powers, but infinite positive power. So these are Lorentz series. So that means now that the divergences have been encoded so as to be poles at 0. So instead of just having infinite quantities, you keep track of what actually happened and get power series or Lorentz series where you have poles here. So now you can manipulate these series instead of just having infinite quantities. The second step is kill the pole part. And here I really need to put that in quotes. So the ring of Lorentz series, it has this operator which returns the pole part. So only the negative powers of this formal parameter. So you would like just to take your Feynman amplitude and then just post-compose with R. So that gives you something which is just a power series now, and now you could evaluate at 0. But this does not work. And one way to see why it does not work is that, well, I already revealed that this is going to be a bialgebra. And the Feynman rules actually have to be characters, meaning they take products here to products here. And that expresses the physical idea that independent processes should have, the amplitude should be the product. So it's really important that they are characters. And if you just do this, it will no longer be a character. So important physical property is lost. So the problem is that graphs have nested divergences. So for example, if I draw a graph here, that's a graph with 3 loops. So it has overall a divergency, but it also has these nested ones. There's one little graph with a loop here and another little graph with a loop here. And you have to handle these sub-divergences before you can do the whole thing. So you need some overcounting, undercounting, like people love in combinatorics. So need overcounting, undercounting. And this was sorted out over a very long time. It took really almost 15 years. So these letters, that's Bogoliubov, Parasiuk, Hepp, and Zimmerman. And this took like this. The first paper is from 55, and the last one by Zimmerman is 69. So they figured out how to do this overcounting and undercounting, giving a recursive way to renormalize in a proper way so that the new renormalized amplitude will be, first of all, convergent, and second of all, it should still be a character. So I cannot even read these papers, but luckily there are mathematicians who distill physics into mathematics. So this is what Kreimer did in 98. He says that all this complicated combinatorics that I didn't even want to write down is governed by a bialgebra of graphs. So recall that a bialgebra is at the same time an algebra and a coalgebra. So the multiplication here is just disjoint union of graphs, and the co-multiplication is the interesting part. That's what disentangles all these sub-divergences So it's given as follows. You co-multiply a graph by summing over all subgraphs. And then you put that subgraphs on the left-hand tensor factor. And on the right, you put the graph obtained by contracting each connected component of the subgraph to a point. So this is written like this. So maybe I should co-multiply this one. This is the only graph I ever draw, so I know it has 5 terms. The first term is if you take out the empty graph, and the last term is if you take out the whole thing. That gives this. And then there are 3 terms in the middle. You could take this one out. That's this little here. And then on the right-hand side, you have to contract all that to a point. You get this. Then you could take this one out. So that will be this. And then on the other hand, here you contract that to a point. Or you could take out both. That's allowed. They are not necessarily connected here. So that will be both. That's this. And then we have to contract each connected component. So that will just be this one. So there are 5 terms in this co-multiplication. And it does precisely convey the intuition that you have to extract divergent subgraphs. Now I write down Bogoliubov's formula in the interpretation of Kreimer. It says first you construct a counter term called. So we start with a Feynman rule phi, and first we have a counter term. And this counter term is equal to 1 if the graph is trivial, and otherwise it's equal to. And now we have this pole part operator, and you sum over all the subgraphs, but we don't want the last one. So you begin to recognize a lot of familiar stuff. Sorry, I need to apply now this one to the subgraph, and then I apply the original one to the quotient graph. And I take pole part of all that. So that's the counter term. And then finally the renormalized amplitude for this graph is you convolve the counter term with the original Feynman rule. And this is convergent, so it's a number and it is a character. So this is Kreimer's reformulation of what Bogoliubov started, and later people sorted out why it works and so on. So you can already see that this is very much like Möbius inversion. So the remaining 5 minutes, I will just explain how to get this by exactly the same proof by definition that I wrote for abstract Möbius inversion. So I should say one thing, that the fact that this is a character again, that's very subtle, and that follows from a property that this operator has. It's the property of being a Rota-Baxter operator. And that's something Baxter, that's not the Baxter from the Young-Baxter equation. It's Glenn Baxter, who worked in probability theory. He was actually a postdoc in Aarhus. So a Rota-Baxter operator on an algebra, it's one that satisfies the following. If you apply it, it's a linear operator, but it's not multiplicative. So the lack of multiplicativity has the following form. It's R, then it's X, R, Y plus R, X, Y. This is the Rota-Baxter equation. And this is the key property to ensure that this one is, again, a character. Okay, now I'll do just the formal stuff. So it's very formal. We start with a character that goes from a bialgebra into a Rota-Baxter algebra. And we assume that phi of group-like is equal to 1. Now we define psi 0 is E. What is E? This is a coalgebra, so it has a map to the ground field, and then there's a unit into here. So this is just, first you do the co-unit, and then you do the unit of A. Okay, and now we do the same thing as before. Take this one, but now we put in this Rota-Baxter operator in the convolution. So this should be now phi minus E. And here, the definition of this one is just the usual convolution, but then you apply the Rota-Baxter operator. So since it's not multiplicative, this is a crazy product. It's not associative, and I don't think it's unital either. So it's not something you would like to use very much, but it's good enough to do exactly all the same things as before. You just need to be careful that you don't associate parentheses. You define these two, and you define this. And the even and odd, you quickly see that this is odd convolution and so on. So in the end, you get exactly the same formula as before, namely E minus R, and then psi convolution phi minus E. This is the same formula as this, by the same argument I gave for Rota's original formula. The E here just says that there's a special case we should take care of. Then there's a minus R, that's this, and then this is the convolution product of the counter term with the original, and we make exception for the last point. The graph is not allowed to be the full graph. And then finally, you want to take this one and convolve with this. It's no longer an inverse, but this is what should be called the renormalized character. Yeah, there's a lot here I should talk about, in particular the role of the Rota-Baxter operator, but I think I just stop with the remark that Möbius inversion in the abstract version is a special case of this, namely where you take the Rota-Baxter algebra to be the ground field with the identity operator. The identity operator certainly satisfies all this. It's a completely degenerate case, so maybe I just write here. Möbius inversion is renormalization by taking A to be the ground field, R to be the identity operator, and the character we start with should be the zeta function. Oops. And then when you do all this, the resulting thing you find is the Möbius function. So Möbius inversion in the end of the day is just a very degenerate case of renormalization. That was a little bit hurried in the end. I'm sorry about that, but some of us have to go to the next event. So I'll stop here.
Thank you very much. Are there any questions, either locally or I guess online? You can also ask questions by either unmuting or writing in chat, in which case I will read it out loud. But maybe there's already some questions. Yeah.
Yeah. Okay. So maybe could you just state what is the statement of the last part? So whenever you start with what is the theorem?
So I think of this as the divergent amplitude. And then from that, I can construct a counter term. That's this one.
So what?
So the interpretation of this abstract Rota-Baxter operator is to go to the pole part. So what it says is that if you cannot just apply it directly, but if you carry it through all the convolutions, then it actually ends up being a character again.
The process that does that is a generalization.
Yes. So in Möbius inversion, you don't necessarily have a multiplication. So in that case, there's no question of character. So it's well, you have to be a little bit more precise to write it as a theorem, but I don't want to do that.
Any other questions? Not locally, I guess. So if somebody online has a question.
Then maybe there are some.
That also, that's just from before, from when the issues. Yeah, so I guess thank you again, Joachim, for the talk.
You're welcome.